Okay, so we've so far focused on uh, relatively simple models of CMOS transistors. And again, the emphasis there was on not so much on calculating precise values, but rather on finding models that capture the interdependency of various parts of a circuit and of a transistor. Um, if we want really accurate values, typically we're going to rely on simulation for that, especially in advanced CMOS technologies. Um, but it's still nice to have the simpler models as an intuitive guide when you're doing design of, let's say, an amplifier and you want to know whether to increase or decrease the size of a transistor. Well, you can, really it's mainly the first order model that's in your mind that you're using to figure out what will be the positive and negative impacts of, say, decreasing the channel length or increasing the gate width, right? But now we're going to talk about a little bit, some more advanced aspects of MOS modeling that are important, that you may not be familiar with, but that are very important for analog design. So first thing I want to talk about is subthreshold operation. So the square law active mode equations that we presented so far implicitly, in fact, presume an effective gate source voltage of at least about 100 millivolts. Um, Once you get below that, the channel region is very weakly inverted, and certainly when V effective drops to 0 or below, then it's really not inverted at all. Um, and yet, some subthreshold current persists. So that current can be thought of as a subthreshold current, also sometimes called a leakage current, especially when we have VGS equal to 0, in which case we would really expect the transistor to be off. And yet still, drain source current will flow if there's a non-zero drain source voltage. Now, in fact, for VDS greater than about 100 millivolts, the current's a very weak function of VDS in general. So it's modeled by this exponential relationship. Now, again, I encourage you to review the textbook to understand this better, but it may not be too surprising that there's this exponential relationship arises, because if you think about a NMOS transistor, for example, that's off or not inverted, in fact, it has an NPN structure. So, and the gate voltage here, even though the channel is not inverted, it's the field effect that's introducing is having an impact on the surface potential in this part of the structure. So you end up with a weak bipolar junction transistor effect happening that gives rise to this exponential relationship between V effective and the resulting subthreshold current. Now, in this expression, you'll notice that V effective can be 0 or even negative, and you will still get a finite current flowing. And it will flow in whichever direction we have a positive VDS. Again, you see no dependence here on VDS because we've assumed VDS is not too small. And yeah, because of this exponential relationship here, if we plot drain current versus V effective or VGS on a semi-log axis, that is, the drain current's on a log scale, but VGS is on a linear scale, then we end up with a straight line here. And the slope of the line is determined by the constant of proportionality in the exponent here, which in this case is Q over NKT. Q is the fundamental electronic charge, K is Boltzmann constant. Importantly, T is absolute temperature, so there's a strong temperature dependence at play here in determining the amount of leakage current or subthreshold current that we see. And then the final parameter is N. N is a transistor parameter that again relates essentially the strength of the gate field effect to that of the back gate. So if you think of the structure up here, you'll realize that there's a gate oxide capacitance between the gate and the surface of the transistor, and then there's a second capacitance here between that surface region and the body terminal of the transistor, which is effectively a reverse biased junction capacitance. It's determined by that depletion region pictured there, and that's captured by this term. So those two series capacitances form a kind of a voltage divider that determines how much the surface potential changes in response to changes in the gate voltage. And so the ratio of those capacitances, which is captured with this expression here, is important in determining the subthreshold current. And that ratio is in turn a technology parameter. It's not something that a designer typically has much control over. Typical value might be 1.5 or thereabouts. But if you can do an experiment and measure subthreshold current and plot it on a semi-log scale as shown in the bottom left here, experiment can be done in a lab or it can be done in simulation. The slope of that line that you get for values of VGS around and below the threshold voltage will allow you to infer that parameter N. The other technology parameter at play here is ID0, and it in turn also depends on technology parameters, carrier mobility, COX. It also depends on N and temperature, as shown over there. Now, the temperature dependence is quite complicated here because it shows up in a couple different places and it's an exponential relationship. But suffice to say that the largest values of subthreshold leakage current are observed at high temperatures. I think that's an important point to keep in mind. And another, important point to keep in mind is that subthreshold current, although it, obviously will be much smaller than the values of currents that we see in triode or active mode for a given transistor, they can be a significant source of power consumption, especially in circuits with large transistors, many of which are supposed to be turned off, but the cumulative effect of all their subthreshold leakage can be a really significant source of power. For example, circuits that are operated only intermittently and are put in standby for long periods of time. For example, that's often the case in devices that are battery operated, where low power, low energy consumption is really critical. In those devices, subthreshold leakage is really, can really be a killer. Now, when I prefer the sort of nomenclature I prefer to use is to refer to subthreshold current as the current that arises whenever V effective is around 0, that is, whenever VGS is around the threshold voltage or below. And I specifically refer to leakage current as the current that arises when VGS is 0. In that circumstance, we would expect V effective to be quite negative. So again, because of that exponential relationship, when VGS is 0, we've got to substitute in V effective equals negative VT. And so even though V effective is negative, you get a finite current. This is really when we most expect the transistor to be completely off, and yet we still have a finite current. one way to reduce leakage current by design is to increase gate length L. And so that's a measure that's often taken in low power circuits to ensure that standby power is kept low. And so far, we focused on the negative impact of subthreshold conductance, but in fact, subthreshold conductance can actually be very useful in analog design. And to see how and why, I think it's useful to go back to this expression over here, which relates the small signal transconductance of a MOSFET to its bias, drain current, and its effective gate source voltage in active mode. Now, remember that this expression illustrates that for fixed bias drain current, we expect transconductance to increase as we decrease V effective. However, you might have noticed already that there's something strange about this expression. It suggests that if we keep bias current constant, but decrease V effective to a very, very small value, even approaching zero, eventually GM will become infinite. And something about that doesn't seem right. First of all, you might wonder, well, how can we possibly do that? If we have a finite drain current, how can we have very, very small V effective approaching zero? Well, the answer to that is you make W over L huge. And if you don't care about the parasitic capacitance, it's not a high-speed circuit, that's actually something that you can do. However, even if you do that, you still don't see that the small signal transconductance approaches infinity. So the relationship presented here is actually plotted for an example transistor on this plot here. So here we've got the ratio GM over ID, right? So we take ID, we move it over to this side of the expression, and what you're left with then is a plot of 2 over V effective. Now we're plotting it versus the gate source voltage, and the threshold voltage is somewhere over here at about 450 millivolts. So it's around here that V effective reaches zero. And as a result, the square law prediction is this dashed line here, whereby we would expect the transconductance, GM, again, for fixed ID, to increase indefinitely, blow up to infinity. So that's what we would expect purely from a square law. But in fact, that's not what you see. What you see is more like what's shown with the solid line here. Around as the gate source voltage approaches the threshold voltage, that is, as V effective approaches zero, it flattens out. And that's exactly what's predicted by the subthreshold current model that we presented on the last slide. That is, according to the exponential uh, voltage current relationship, if we take the derivative of that, it ends up looking just like the relationship for the small signal transconductance of a BJT. You get an expression like this, where you've got the bias current in the numerator, and you've got a term here, KT over Q, that looks just like the thermal voltage. Remember, it's about 25 millivolts at room temperature. KT over Q, just like in a BJT. The only extra term compared to a BJT is this factor N, which we described previously. It's a number not so far from unity. So you have a small signal transconductance very similar to that of a BJT, in fact. So you'll notice this expression, um, you know, uh, becomes independent of V effective. So the moral here is that if V effective gets very, very small, GM over ID approaches a constant Q over NKT. And that's exactly what you see in these simulation results here for a MOSFET. And uh, in fact, a plot like this is very useful in allowing us to determine approximately what's the value of N. So it's very useful. We've been showing lots of these plots throughout this video, where we plot very simple currents and voltages while we sweep certain voltages in the transistor biasing and maintain others constant. These are very useful simulations to do when you're just starting analog design with some MOSFETs because, first of all, they allow you to validate the models that you're using. For example, if you don't see this behavior at very low values of V effective and negative values of V effective, this should flatten out at a value that makes sense around, around the thermal voltage. If you don't see that, then there's something wrong with your model. Maybe it's not modeling subthreshold leakage properly. Um, the other thing it lets you do is lets you get a feel for and extract the transistor model parameters, things like the value of n, um, mu n, cox, all these constants can be estimated by performing simulations. Now you might say, if you have the transistor model for your simulations, why can't you just kind of look those values up directly in the model? Well, modern MOSFET models are so complicated. In order to properly capture second, third, fourth order effects, all temperature coefficients and so on, MOSFET models and modern technologies contain literally hundreds of parameters. So um, it can be quite difficult to infer what's really the value of any given uh, you know, square law model parameter just by looking at that model file. Especially, you most likely want to know what it is around room temperature for typical device sizes, not for huge devices, maybe not for tiny devices. So sometimes often the easiest way to do that is to just run a series of simulations. And again, that also lets you kind of pipe clean your simulation process in your models and make sure that there's no funny business there. So again, when you consider the lesson here from this plot, it's that if you are limited to a fixed bias current, right, and you might be limited to a fixed bias current because you don't want to consume more power, um, then really the most transconductance you can get from a MOSFET, and probably the most gain, therefore, will be obtained by making V effective small, approaching zero, but that and you do so by making the transistor W over L ratio very, very large. But beyond a certain point, there's a point of diminishing returns here, and that happens at values of V effective right around the thermal voltage. So we can infer that by calculating what's the intersection of this plot here, and this is a plot of 2 over V effective, and what's the intersection of that and the plot of Q over NKT? The place where these two limiting expressions intersect, that's going to give us a good feel for where this breakpoint occurs, the sort of transition from a square law model to um, weak inversion and subthreshold conduction for negative values of the effective. And we know that, again, at room temperature, um, this value, we know more or less what this value is. It's a very small value, kind of 50 millivolts or less. So once we get to that point, there's, sort of, it's a point of diminishing returns. There's not much point making the transistor larger and making V effective any smaller than that. All we're doing is making the transistor even bigger for very little further improvement in GM. Um, so this can be a useful sort of bias point. If we don't care much about speed and we have the freedom to make the transistor very large, we don't care about parasitic capacitances, but we do want a lot of gain, then we will likely want to bias the transistor with an effective gate source voltage somewhere around this breakpoint that is very small value, kind of on the verge of weak inversion. So we also observe non-ideal phenomenon when we have very large values of VGS and correspondingly large values of VDS, keeping the transistor in active mode. And these are going to cause the voltage current relationships of the MOSFET to deviate from the simple models we've presented so far. And there's a variety of physical factors that cause this deviation, and we're going to refer to all of them collectively as mobility degradation, because that's the way we're going to model the effects. But essentially, when VGS and or VDS are very large, and especially when the transistor dimensions are small, we're going to see very high electric field strengths um, acting on the MOSFET, and the lateral field which is the electric field acting along the length of the channel between drain and source, is going to be strong for small values of length L and large values of VDS. And that's going to accelerate carriers up to their saturation velocity, even for values of VDS below V effective, which we usually associate as the saturation voltage. Moreover, if we have large values of VGS far exceeding the threshold voltages, we're going to see a strong vertical field acting across the gate oxide, and that's going to act on carriers flowing down the channel and cause them to interact with imperfections at the surface of the semiconductor material, and it's going to slightly disrupt the current flow. And again, all these effects act to reduce the current below what is predicted by our simple square law models in active mode. So these reductions in current can be modeled by a reduced carrier mobility. And the expression for modeling an effective carrier mobility is shown here. So essentially, it's the sort of nominal carrier mobility that is associated with the transistor's operation at more moderate values of V effective. But then with this denominator term that is greater than 1 and increases with increasing V effective, that causes the effective mobility to decrease below its nominal value for large values of V effective. And there are essentially two fitting parameters here that allow us to properly model this effect, theta and m. And so the effects are illustrated here. For example, here's a plot of drain current on the y-axis versus gate source voltage on the x-axis for a typical, for an example NMOS transistor. And again, it's the same one that we showed a plot for before, where the threshold voltage is somewhere around 450 millivolts. And by a straight square law model, we would expect a quadratic relationship here beginning at the threshold voltage. That would look like this. So you see this quadratic here provides a good fit over a range of V effectives up to 2, maybe 3, maybe 350 millivolts. But beyond that, for V effectives exceeding 400 millivolts or more, you see that the real current, which is the solid line here, is less than that predicted by the square law model. And that's the onset of mobility degradation in this case. This effect can also be seen perhaps more clearly with a plot of transconductance versus VGS. So this plot is essentially the derivative, a plot of the derivative of this curve versus VGS. So you see in the square law region, okay, then we expect transconductance to increase linearly with V effective. That's because in this case, the transistor dimensions are not changing as we change VGS. It's just one fixed transistor. We're sweeping VGS. So remember, in that case, GM increases in proportion to V effective according to the square law. And again, we see that over a range of a couple hundred millivolts. But that for large enough values of V effective, the curve starts to flatten out because the current is less than that predicted by the square law model. So this plot, I think, illustrates it very clearly. And this equation here predicts that at very large values of V effective, this term here will predominate in the denominator, and you'll end up with an effective carrier mobility that's inversely proportional to V effective. And as a result, that'll basically cancel one of the V effectives here in the numerator in the expression for drain current, and you arrive at eventually a linear relationship here between drain current and V effective in the limit of very large values of V effective. And so a linear relationship implies, therefore, a constant slope or constant GM. And that is given by this expression here. So again, we can estimate the effective gate source voltage at which this transition occurs, at which mobility degradation effects start dominating. We can estimate the V effective where that occurs by finding the intersection between these two curves. the upper limit here, the limiting value here, um, tells us, which we can infer from where the plot ends up for very large values of V effective, and that gives us this expression here. And if we fit a straight line to the linear portion of the curve, that the slope of that portion of the curve is predicted by the square law model, and equating those, we can solve for V effective, and it turns out the intersection occurs at a value of 1 over 2 theta. So fitting a straight line here and a sort of horizontal line here, finding their intersection, and then from that intersection we can infer the model parameter theta. And then we just need to play with m until a good fit is obtained with the simulated or measured results. So if you look closely here, there's a dotted line. That's basically the fit that's obtained here using this mobility degradation model. So in summary, let's recap the different MOS operating modes that we talked about. In summary, we've shown that the square law that we're most familiar with is really valid only in active mode over a fairly modest range of values for V effective. So once we get to values of V effective below 100 millivolts, certainly below 50 millivolts, we start observing a voltage current relationship that's more closely predicted by the exponential relationship for subthreshold. So the sort of square law regime is bounded on the lower side at V effectives of about 50 or 100 millivolts. And on the upper side, it's bounded by this technology parameter 1 over 2 theta for V effective. And that can be as low as a few hundred millivolts or even lower. So really the range of V effectives over which we observe a real square law can be very small for very advanced, very short channel length devices. Now the range can be large for long channel length devices, but it's really for technologies at 180 nanometers and below. We might see the square law model persist only over a couple hundred millivolts and even less. Um, and then exceeding, for V effectives exceeding that upper limit, we enter this mobility degradation region where instead of a square law, we've really got a linear voltage current relationship. So some important lessons for analog design. Remember that subthreshold operation provides us the highest transconductance for a fixed current. And so therefore, subthreshold operation can be useful when bias current is limited, that is, when we're trying to operate with very low power, and when we don't require high speed, we can tolerate very large transistors with large parasitic capacitances. So low power, low speed operation, we may often be biasing our signal path transistors right on the verge of subthreshold here. We may not go much beyond that, again, because we get diminishing returns there. On the other hand, when we're interested in very high speed operation, we're more likely to operate up here, because essentially that's where we're using the smallest possible transistor while getting the most possible GM, the most possible transconductance out of that tiny transistor. So you pump a lot of current through a transistor with a small W/L ratio, you inevitably will have a relatively large V effective. But there's not much point pushing far beyond, far deep into mobility degradation, because again, remember that GM plateaus and doesn't, increase for large values of V effective. So essentially, there may be special cases, but a lot of normal analog design occurs over this very relatively narrow range of values for the bias point of V effective. Um, and so in a way that I think that helps focus your design effort and you know, uh, sort of limits, gives you a guide for selecting operating points for all the transistors in your circuit. You always, you keep this picture in mind and think, for this particular transistor, do I want a lot of transconductance? Do I care how big it is? Am I really limited by power, so I don't want to bias with a lot of current? If the answer is yes to these questions, then probably I should size it so that it's on the verge of subthreshold. On the other hand, if it's a very high speed, I really need a very high speed from that transistor, I'm more likely to bias it up here with a larger value of the effective, close to mobility degradation. And you will know what these numbers are because, again, you'll do your pipe cleaning simulations with the transistors right at the start of the design process. If you want any kind of compromise between those two extremes, well, then you're limited to this relatively narrow range of values of the effective. Again, for older technologies and long channel length devices, the range over which the square law is observed may be large, but in advanced technologies, it may be only a couple hundred millivolts. And this table is a useful summary of the relationships that we presented in all these regions. We've got the exponential voltage current relationship in subthreshold. The square law is our sort of normal active mode operation, also called strong inversion. And then for larger values of V effective, we start seeing mobility degradation. And in that case, the voltage current relationship is linear. And the regions of validity of each of these operating modes is defined as shown here. V effective for the square law is bounded within this range here. And again, takeaway point is subthreshold operation can be most useful when very low power operation is required, whereas operating around mobility degradation limits can be useful for very high speed operation. And most of normal analog design takes place sort of swinging between these two limits and trading off speed versus power. Now, we focused so far on subthreshold leakage, um, but there are other leakage currents that may be of interest as well. And these are additional non-ideal phenomenon that are good to be aware of. So I should at the start point out that subthreshold leakage, which we've already modeled, is usually the largest of these leakage currents, but sometimes these others can be problematic for other reasons. There is it's a finite, although very small gate leakage current that flows, especially in transistors in advanced technologies where the gate oxide is extremely thin. So in such cases, a finite, you can model that as a finite current that flows into the gate, um, and that current is proportional to the gate area and also increases at high temperature. You've also got a finite leakage through all reverse bias PN junctions, and there's several of them in a typical MOSFET. Right? So from source to the body, from drain to the body, you may see additional leakage currents flowing. Again, these are likely to be proportional to the area, the surface area of the PN junctions. All of these leakage currents are increased at more advanced technology nodes where smaller dimension transistors are used. And in analog circuits, although in digital circuits, leakage current can cause really big problems because digital logic circuits can be large and comprise billions and billions of transistors. So even a small amount of leakage current from each transistor can really add up. In analog circuits, especially analog circuits that are powered on and operating, there's usually more current being burned elsewhere in bias currents than all the leakage currents added together. But leakage currents, even in that case, may be important for their impact, for example, on sampled analog voltages. We may have examples of simple circuits, something like this, where a MOS transistor is being used as a switch to have a voltage preserved on a capacitor. The transistor is turned off, the switch opens, and we expect that the sampled voltage will be held on this capacitor C hold over here. But because of finite leakage currents in the MOSFET, that voltage that's sampled on V prime may degrade over time. So, it may not even be a power consumption issue. It may actually be a performance issue that makes us care about leakage currents. And finally, just a reminder, leakage currents increase dramatically with absolute temperature, in fact, exponentially. So if you're considering a circuit where leakage currents may be an issue, maybe a problem. If you want to simulate the worst case, you really need to go and set the simulation setting to the maximum operating temperature that's of interest. There's additional effects that arise in very small dimension transistors. In fact, the transistor threshold voltage itself depends on uh, the transistor dimensions, W and L. Again, these are some of the reasons why transistor model parameters can get so complicated. They need to capture all these effects. So you can imagine if the threshold voltage changes, that's going to have an impact on virtually everything we care about. Drain currents, transconductances, and we need complex models to capture that. There's several other short channel effects that cause the drain current to increase at relatively high values of VDS. So, one significant one is called drain-induced barrier lowering. Um, what this does, and it's particularly prominent when you have very small channel lengths L, it means that variations in VDS can affect the carrier concentration over a significant fraction of the channel region. So really what you have is, if you're affecting the carrier concentration here, you're effectively changing, and in fact, you're most likely lowering the threshold voltage when VDS is very, very large. So you've got this sort of compounding effect where VDS increases. Not only do you see the typical effect you expect to see in active mode, but at some point, not only that, the threshold voltage also starts decreasing. And that's where you get increasing, the currents start increasing further. There's other phenomenon that show up in short channel transistors and at high values of VDS, especially, that cause current to increase. But drain-induced barrier lowering, also referred to as DIBBLE for its acronym, is really one of the biggest, and special processing techniques that are in fact applied in modern nanoscale CMOS transistors to mitigate drain-induced barrier lowering. So specifically, the regions right at each extremity of the channel region are implanted so that they're more lightly doped than the rest of the drain and source region. And so this so-called lightly doped drain region, but of course it's applied on both sides of the channel, LDD, um, tries to mitigate the impact, the possibility of drain-induced barrier lowering um, in these advanced technologies. Unfortunately, these lightly doped drain regions also introduce a significant additional resistance. Remember, if you have a lightly doped region as part of your drain conduction path, and you've also got one over here at the source, that's going to be a little bit of extra resistance that's directly in series with the channel. So if you consider the T model here, it's like adding an extra small resistance right here in series with the source in particular. You may also want to model one up here, but it's really in active mode, this one, that's likely to be more problematic. This extra series resistance due to the LDD uh, basically shows up in series with, in the T model, with our small signal 1 over GM resistor. So it effectively reduces the value of GM of the transistor. The small signal VGS that's applied between here and here now is partly lost across the LDD resistance. And so that reduces the amount that shows up here across RS, and which then gets multiplied by GM and turned into small signal drain current. So I mentioned in the past that it can be really useful to do some pipe cleaning simulations when you're starting design, especially in a new technology. And just to get familiar with your transistors, you really want to know your transistors when you're starting a design so that you can quickly on the back of an envelope make estimates and trade-offs and calculate rough device sizes. So I just show you here examples of some simulations you can perform on transistors to help you get comfortable with them and extract some of these model parameters. Again, the motivation here is that modern SPICE model formats often have hundreds of parameters in order to match all the operating characteristics of the transistor in the presence of variations to capture high order nonlinearities, temperature effects, sizing effects, proximity effects. And models like that are just too complex to be of use in the early stages of circuit exploration and design. We need to go through this process of extracting a simpler first, second order model of the transistor parameters to allow us to draw some intuition from these complex channel models. So the way this would typically be done would be to characterize a nominally sized device, and then that may comprise many fingers, and then normalize the parameter values appropriately to obtain a per finger model that can be scaled for modeling transistors of any size. So to be clear, let's say in a design you're anticipating using transistors with gate lengths that are 2 times the minimum gate length, and perhaps you're going to use some transistors that are 1 times the minimum gate length. So you might want to separately, I would recommend you separately characterize the minimum gate length transistors from those with larger than minimum gate length. And the reason is that often at the very, very minimum gate lengths of any technology, especially those in 180 nanometer gate lengths or below, you often see changes in some of the model parameters. So you don't want to apply model parameters that are extracted with minimum gate length devices to non-minimum gate length devices. So you might create a couple different test benches. So here in this one, we're focused on transistors with gate length 2 times the minimum gate length. And you'll just pick some nominal value for the width. In this case, it's relatively large. I chose W over L ratio of 120. A W over L ratio like that would normally be broken up into many parallel fingers, as discussed earlier. In this case, I've broken it up into 15 parallel fingers, each one with a W over L ratio of 8. And then I'm going to do a bunch of characterization on this multi-finger transistor, to find things like the parasitic capacitances of it, the mu NC ox, estimate a value for mu NC ox for it, um, and all the other, the body effect parameters, whatever it is you might be interested in, threshold voltage and so on. And then, if in my design, then I'm going to end up having a transistor that's maybe twice this size, then I can just, apply, twice this width, but the same gate length. I can just apply the same transistor parameters, but doubling those that are proportional to W over L, such as parasitic capacitances, for example. Now, the reason you don't want to characterize just one finger is because, as we showed before, when you have a multi-finger transistor, you get to share a bunch of source and drain regions, and that reduces the associated parasitic capacitances. So if you characterize a one-finger transistor, you're probably overestimating a lot of the parasitics associated with it. So it's better to, and in analog design, you won't often be using a single finger transistor unless it's a very low power or very tiny circuit. You're often going to require more current than that than can be handled by a single finger transistor. So, again, and you want to characterize a few different gate lengths here. Here I'm suggesting maybe the minimum gate length, 2 times the minimum gate length, 10 times the minimum gate length, and you have sort of 3 sets of model parameters that you can apply to the rest of your design. So in order to estimate the transistor small signal transconductance and threshold voltage, you can just do a simple simulation where you bias the transistor with a relatively high drain source voltage so that it doesn't enter triode, and just sweep VGS. And you should obtain, you would expect a square law model and, and you can take the derivative of that, and you end up with a plot on the right of small signal transconductance versus VGS. Uh, and from that plot, you can find the point where the linear part of the curve intersects um, the abscissa, and that intersection will allow you to estimate the threshold voltage. In this case, it happens around 0.45 volts, whereas you know, the point at some point for a large value of V effective, you're likely to see the curve depart from the square law, and that's really marking the onset of mobility degradation. In order to extract small signal parameters like RDS and the associated lambda, uh, you know, you'll want to do a simulation where you apply gate source voltage, a constant gate source voltage to the transistor that exceeds its threshold voltage, and sweep VDS, and then plot ID. So again, you expect then to see a plot like this for small values of VDS. You will see the transistor in triode. The slope here can also be useful for inferring some transistor parameters. So um, that's something that can be very useful, especially, and that value may be even more useful if most of the transistors in your actual circuit are going to end up being used in triode mode. But if you're interested in RDS in active mode, then you may be interested in characterizing the slope over here. Now, I will say that generally trying to extract RDS and lambda is more problematic than extraction of GM and VT. You may see that if you try and do this yourself. It's just that this curve here, for reasons we've already discussed, is not very linear. It's not perfectly approximated by a straight line. So if you take the derivative of this curve, you won't see it really approach a constant value anywhere, most likely, unless it's a very long channel length device. Instead, you're more likely to get a plot like this, but then you can just have it, you know, fit an approximate value for lambda here for, you know, the values of VDS that you expect to see most of the time in your circuit. And again, this is meant to provide you with an approximate transistor model that's useful just doing first pass design. You're not going to use these model parameters to calculate accurate values such as power consumption or gain of a circuit. You're going to rely on SPICE simulations to tell you that. And so here's some more detailed analysis and a link to sort of netlist examples of how these sweeps can be done. And the resulting plots you see, they, you know, mirror very closely the cartoons that I was showing in the past. Here is showing an example of finding the threshold voltage and using the slope of this part of the GM versus VGS curve, you can estimate the constant mu NC aux. Here we continue that plot up to higher values of VGS, and indeed you see the onset of mobility degradation. You see transconductance approach a constant value for high values of VGS. That constant value can be used to infer theta, one of our mobility degradation parameters. And you can also, you know, using this, the extrapolation of the square law part of the curve up to that constant value, you can also find that intersection. In this case, it's around 700 millivolts, which represents the gate source voltage at the onset of mobility degradation. Here are plots that where VGS is being held constant and VDS is being swept, and you see here in active mode, fairly straight line, which can be used to find RDS and hence lambda of this transistor. Again, remember that lambda depends strongly on L, so the value of lambda will be different when you rerun the test bench for different values of gate length.